There are many real-life applications for a sinusoidal function, which can allow one to determine many different characteristics of many different scenarios.
However, how is it possible that a Ferris wheel, such as the London Eye, can share a common characteristic with a sinusoidal function?
The London Eye is a magnificent structure constructed in 1999 as the world's first observational wheel. As a result, it was considered the tallest Ferris wheel at that specific time.
Annually, the London Eye attracts around 3.5 million tourists per year.
In order to determine the relationship between the London Eye and a sinusoidal function, we must consider its features.
When examining a sinusoidal function, one must consider its main feature. The sine or cosine function is a consistent periodic wave which reaches a minimum and then a maximum point between regular intervals.
Referring to this graph, one can see that the cosine graph has a consistent amplitude, axis, throw, peak, shifts, reflections, and stretches or compressions.
Before determining the appropriate equation that models the movement, we must gather the required values and dimensions of the London Eye.
The height of the Ferris wheel from the ground to its maximum height is 135 meters. The diameter of the Ferris wheel is 120 meters. The radius is 60 meters. The circumference is 377 meters. The speed of the Ferris wheel is 21 centimeters per second, or 0.8 kilometers per hour. The maximum point is 135 meters, and the minimum is 15 meters. And also the period is 30 minutes. This diagram is a representation of the different dimensions of the London Eye.
The axis can be determined by taking the average between the maximum and minimum value of the Ferris wheel. So we take 135 plus 15, which equals 150, and then divide by 2, which gives you a result of 75 meters.
The amplitude or vertical compression can be determined by taking the difference between the maximum and the minimum value of the Ferris wheel. So we take 135 minus 15, which gives us 120. Then we divide by 2, which is 60 meters.
The vertical shift can be determined by taking the position of the axis of the parent function and translating it to the Ferris wheel's function. So we take 0 plus 75, which is equal to 75.
The horizontal compression can be found by dividing 360 by the period. Therefore, we do 360 over 30, which equals 12. The 12 shows that the Ferris wheel's function completes a period 12 times faster than its parent function.
In this scenario, there is no horizontal shift.
The reflection can be determined by how the function is set up to commence. For instance, since a Ferris wheel begins at a minimum point, a reflection of the cosine wave along the x-axis will produce an optimal graph.
Given all the values we have determined, we can assemble the separate parts of the equation into an entire equation.
The general or parent equation of the cosine is y is equal to a cos bracket k bracket x plus d close bracket minus c. Now by inputting all the values we get the equation h of t is equal to negative 60 cos bracket 12 bracket x plus 0 close bracket plus 75.
As the London Eye operates from 11 a.m. to 8:30 p.m., the Ferris wheel is operational for 630 minutes per day. Therefore, the realistic domain of the function is d open set t such that t element of real numbers. 0 is less than or equal to t, which is less than or equal to 630. This is the optimal as the x value, or a time of 630 minutes, of the Ferris wheel completes 42 cycles and returns back to the minimum value.
Created using Powtoon.